Hello everyone, today we're going to look at curve sketching. So recall from before that the derivative is the same thing as slope, which means that if the derivative, aka the slope, is positive, the function is increasing. If the derivative is negative, the function is decreasing. If the derivative is 0, that means that the function flattens out. So we can ask questions like, where is the function y equals 8x squared plus 9x increasing? This is the same thing as asking, where is the derivative positive? So before we can answer this question, we need to find what's called the function's critical points. A critical point is where the derivative is 0 or undefined. So we're going to be working mostly with polynomials, so it will really just be 0. But in general, it could also be where the function is undefined. So I take y prime, so that is 16x plus 9, and we're going to set it equal to 0 and solve for x. So 0 equals 16x plus 9, which means x equals negative 9 over 16. Next, we're going to do what's called the first derivative test. So the first derivative test starts with a number line. On this number line, I'm going to plot all of my critical points. So I have only one in this case. So I'll put it in the middle. Okay, so negative 9 over 16. I'm going to put a 0 above it because the first derivative is 0 at that point. Okay, so remember, this is called the first derivative test. I'm only dealing with the derivative in this case, so not the original function, just the derivative. Okay, so once I have all of my critical points plotted and I put a 0 above them, I then have to take any point between my critical points and, off to infinity and off to negative infinity. So I'm going to pick a number to the right of negative 9 over 16, say 0. So I plug in 0, again, into my derivative. And I want to know, is that positive or is that negative? I don't care the actual value. I just need to know if it's positive or negative. So I plug in 0, I get 9, which is positive. So to the right of my critical point, I'm going to put a plus sign. And then I do the same thing for the other side. I'm going to choose a number that's to the left of negative 9 over 16. So let's do negative 1. So I plug in negative 1. So 16 times negative 1 plus 9, that's a negative number. So I put a negative sign. Okay. And again, if I had another critical point, I'd have to test another point. So what this is saying is that everywhere to the right of negative 9 over 16, my function's derivative is positive, which means the function's increasing. If it had at some point further down the line gone negative, it would have had to have hit 0. But I know that this is my only critical point. So it can't go back down to negative because it never hits 0 again. Conversely, everything to the left of negative 9 over 16, so everything less than negative 9 over 16, has a negative slope, which means the function is decreasing. And again, it can't have gone positive further down the line because it would have had to hit 0. Okay. So then after we do this first derivative test, we go back to the question, where is the function increasing? So that is, where is my positive or my plus sign? So again, that's greater than negative 9 over 16. So my answer would have been, if I have room for it, I'll put it in blue, x greater than negative 9 over 16. Okay? So it's always going to be a range of values. You can either use the inequality notation or you can use set notation. So if I wanted to use set notation, I would say negative 9 over 16 to infinity. Open parentheses. Right, remember, open parentheses means not including that point, but everything up to it. So at negative 9 over 16, the derivative is 0, so I can't include it. So I've got my open parentheses there. Okay, let's try another one. Where is y equals x cubed minus 6x squared increasing, and where is it decreasing? So the first thing I have to do is find the derivative. So we should be getting 3x squared minus 12x. We set it equal to 0, and we solve. So now I have a quadratic. Remember, there are two ways you can solve a quadratic. One is factoring, if it's factorable. The other is the quadratic formula. Depending on the function, it might be factorable, it might not. But you're in calculus, so it's assumed that you know how to solve a quadratic. In either case, remember, you want 0 on one side, which it already is. So do not move a constant over to the other side if there is one. You need 0 on one side if it's a quadratic. So this function is hopefully obviously factorable. There's only two terms. So I'm going to factor out the GCF, which is 3x. Now remember, if something times something is 0, one of those somethings has to be 0. That's the only way you're going to get a 0. So either 3x equals 0 or x minus 4 is 0. So I solve each of those, and I get 0 and 4. Okay. Next, we're going to do the first derivative test. So again, I start with a number line, and I'm going to plot my two critical points. Make sure you plot them correctly, right? The bigger numbers go to the right, the smaller numbers go to the left. So 0 first and then 4. They each have a 0 above it because the first derivative is 0, right? That's how I found those numbers. Then I'm going to take a point to the left of 0, a point between 0 and 4, and a point to the right of 4. So let's try negative 1. If I plug in negative 1, do I get out a positive number or a negative number? Now, the way that I typically do it is if it could have been factored, I'm going to plug it into the factored form. So I'm going to plug my numbers into here because, again, I don't care what the actual value is. I just care if it's positive or negative. So if I'm going to plug in negative 1, I have 3 times negative 1 times negative 1 minus 4. So 3 is positive, negative 1 is negative, negative 1 minus 4 is negative. And if I have a positive times a negative, I get out a positive number. So I know that if I plug in negative 4, I get negative 1. Now I plug in a number between 0 and 1. So let's plug in 1. Again, 3 is positive no matter what. If I'm plugging in a positive 1, then x is positive. And if I'm plugging in 1, 1 minus 4 is negative. Okay, so positive, positive, negative, that's a negative number. For my last one, I'm going to plug in a number bigger than 4, say 5. So again, 3 is positive. 5 is positive if I plug it in for x. And 5 minus 4 is also positive. So that's the 3, the 5, and the 5 minus 4. Positive, positive, positive. I know the number is positive. Again, I don't care what the number is. I just care that it's positive. Okay. So once I have that, then again I go back to the question. It says, where is this function increasing? So it's increasing on numbers less than 0 and bigger than 4, and it's decreasing between 0 and 4. And again, I can write that as an inequality or as a set notation. So as an inequality, I have y is increasing on x less than 0 and x bigger than 4, and y is decreasing on 0 to 4. So if I wanted to use set notation, x less than 0 would be negative infinity to 0. X greater than 4 would be 4 to infinity. And between 0 and 4 looks like a point, but it's the set 0 to 4. Okay, so either way is fine. Now we're going to move on to more of what we need for the graphing part. So critical points are classified as local or relative minimum, local or relative maximum, or neither. What they are depends on what the first derivative test looks like. So if I have my first derivative test, and we call it CP for my critical point, so whatever my critical point is. If to the left of it is positive and to the right of it is negative, that means that my function was first increasing and then flattens off and then decreases. So I have a maximum. If on my critical point it is first negative and then positive, that tells me that my function was decreasing, flattens off, and then increases. And that tells me that I have a minimum. So if my signs change, I go from positive to negative or negative to positive, that's going to be a maximum or a minimum, depending on which one it starts with and which one it ends with. And then if the sign doesn't change, then it's neither a maximum nor a minimum. So if it doesn't change, we have two options. Either it's positive and stays positive, so I get something like that, or it's negative and stays negative. Oops. In which case, it looks something like that. Okay, so if I look at the first derivative test, I can tell right away whether my critical point is a local max, a local min, or neither. So we're going to use that to sketch the graph. So what we're going to do is we're going to find the critical points. And so far all we've done is found the x values. The critical points are a point. It's x comma y. If I want to graph it, I need to know x and I need to know y. So after we found the critical points, we will have to plug it back into the function to find y. We're also going to find the intercepts. Remember, the intercepts are when either x is 0 or when y is 0. And then based on those, and whether our critical points are local max, local min, or neither, we're going to sketch the graph. Okay, so for our first one, we have y equals x squared plus 5x plus 6. So first we're going to find the intercepts. So I'm going to plug in y is 0 to find the x-intercept. Now the x-intercept, depending on what your exponent is, you can have up to that many. So this is a quadratic. I can have up to 2 x-intercepts. So again, I have a quadratic and I have to solve it. So I can either factor it if it's factorable or use the quadratic formula. So this guy happens to be factorable. So I'm going to use that. Right, I need two numbers that multiply to 6 and add to 5. So that's 2 and 3. So if I solve my first one, 0 equals x plus 2, I get negative 2. And if I solve the second one, x plus 3 equals 0, I get x equals negative 3. Now remember, these are points. X is negative 2, y is 0. X is negative 3, y is 0. So those are my x-intercepts. My y-intercept is even easier because x is 0. So if x is 0, I'm left with 6. Okay, so you got to remember going back to when you first learned solving quadratics here. We're going to be doing a lot of quadratic solving. So those are my intercepts. So I'm a little neater down here. Next, we're going to find the critical points. So we take the derivative, so 2x plus 5, set it equal to 0, and solve. So x is negative 5 over 2. Again, we need the y value of it too, so I'm going to plug that in. So remember, it's x comma y, so I need to go back to the function, not the derivative, which I already know is 0. Right? I need y, not y prime. So we're going to plug that into our function. And just be really careful, make sure you use parentheses when you need to if you're plugging it into your calculator. Okay, we find that value, and it happens to be -1/4. So our critical point is at -5/2, comma, -1/4. And then we need to determine whether it's a local max or a local min. So I'm going to make my number line. I'm going to choose a number less than -5/2. So this is where it's a good idea to know what this is as a decimal. So remember, this is -2.5. So I'll plug in -10. So going back to my derivative, which I have erased. If I plug in -10, do I get out a positive number or a negative number? Hopefully we can all agree that that's going to be a negative number. Okay. If I choose a number bigger than -5/2, say 0, whenever I can, I'm going to plug in 0 because it's the easiest. So if I plug in 0, I get a positive number. So my critical point goes from a negative to a positive. That makes it a local min. And then what's left is to sketch the graph. So I'm going to find my intercepts, so we'll call that 6. We'll call that -2, -1. I'm going to use some nice points there. So those are my intercepts. And then I've also got my critical point, -2.5, comma, -1/4. So my critical point is I'm always going to have a critical point between my x-intercepts because I can't go from 0 to 0 without having either a local max or a local min. So in this case, it's a local min, and we'll call it right there. So we'll call that -1/4, and then hopefully you can see it's between whoops. I wrote -1 and I just realized that. Let's see if I can erase that. Right, that should very clearly be -3. So let's try that again. Now we can clearly see that my point's x value is -2.5, y value -1/4. So I have my 4, excuse me, I have my 4 points. Looking at the picture, hopefully it's easy to see that my critical point has to be a local min, so I did everything correctly. So I'm going to connect those guys, and then I'm going to connect up to my y-intercept. I know it keeps increasing, and I know from -infinity up to -2.5, my function's decreasing. And it looks like this. And hopefully we are aware that that is, in fact, a parabola because we have a quadratic. Okay, so you always want to make sure your answer makes sense. Okay. Let's try another one. Y equals x to the 7th minus 16x to the 5th. So again, we're going to start with intercepts. If y is 0, or rather if x is 0, let's do this guy first. If x is 0, then y is also 0. So we have the intercept of the origin, 0, 0. If y is 0, then I've got, again, a binomial, and the only way that I can factor a binomial is GCF and see if it's a difference of squares. So I have a GCF, so I'm going to take that out. So that's x to the 5th. I'm left with, whoops, I'm not left with that. I am left with x squared minus 16. Again, that binomial, I can either have a GCF or it's a difference of squares. That's the only way I can factor a binomial. and that happens to be a difference of squares. That's not a very lovely looking 4. I'll try that again. So x squared minus 16 is x plus 4 times x minus 4, right? The square root of the x squared, the square root of the 16, plus or minus. So setting each of those 3 factors to 0, this guy will give me the origin that I already have. This guy will give me negative 4, comma 0. And then x minus 4 will give me 4, comma 0. So again, I can have up to 7 x-intercepts. I have 3. So 0, 0, 4, 0, negative 4, 0. Next, we have the critical points. So y prime equals 7x squared minus 80x to the 5th. Again, we're going to set that equal to 0. It's a binomial. Again, I'm going to factor out everything I can. And that's not to the 5th, that's to the 4th, excuse me. So when I factor it out, I can factor out next to the 4th. And I'm left with 7x squared minus 80 equals 0. So either x to the 4th is 0, which is 0, 0. So my intercept happens to also be a critical point. Or 7x squared minus 80 equals 0. So that means 7x squared equals 80, x squared equals 80 over 7. And then this is the part that's really, really important because this is the part that I see people mess up. When you have x squared equals a number and you're solving for x, you have 2 answers. X is plus or minus the square root of 80 over 70. Do not forget the negative square root also. Okay, that's really, really important. So we've got, again, 3 critical points. We've got the 0, 0 from before, and then we've got the square root of 80 over 7 with some y value, and negative square root of 80 over 7 with some y value. So when we figure out whether it's a minimum or maximum or neither, we're going to have to plug these into the calculator so that we know roughly what they are, so that we know we're taking points to the left and to the right. But for now, I want you to make sure you're using that whole number when you go back to plug it into y. So make sure you're, saving that root 80 over 7, and I didn't put the square root over the whole thing. Right? That 7 is also inside the square root. So I want you to practice. Plug in root 80 over 7, raise that to the 7th, and then minus 16 times root 80 over 7 to the 5th. Do the same thing with the negative one, and then those will have to round because they're not going to be very pretty. But if we do it, we should be getting these 2 guys. So root 80 over 7 is roughly 3.38. So we have the negative, we have the positive. When I plug those into y, I'm going to get the same number, but again, one's positive and one's negative, and they're actually going to be flipped. Okay. So those are our 3 critical points, and then again, we have to determine whether they're max, mins, or neithers. So we're going to use the number line, the first derivative test. 0's in the middle, negative 3.38, positive 3.38. Oops, that's a 0. Again, I'm going to bring back my y prime, and I'm going to bring up the factored form. So we get x to the 4th times 7x squared minus 80. So again, I'm using the factored one because I don't care what the value is, I just want to know if it's positive or negative. And the really nice thing about x to the 4th is that no matter what number I plug in, that's always positive. So x to the 4th is always positive. So I really just care about what happens to 7x squared minus 80. Is that positive or is that negative? Okay, so I'm going to plug in a number to the left of negative 3.38. How about negative 20? If I square negative 20, multiply it by 7, and subtract 80, is that going to be a positive number or a negative number? So remember, negative 20 squared is 400. And hopefully we can agree that 7 times 400 minus 80 is a positive number. The same is going to be true if I plug in positive 20. Positive 20 squared is 400 times 7 minus 80 is definitely a positive number. So I've got all the way to the left and all the way to the right done. They're both positive. Now let's plug in, say, negative 1, so a number between negative 3.38 and 0. So if I plug in negative 1 squared is 1. 1 times 7 is 7, and 7 minus 80 is definitely a negative number. The same thing is going to happen if I plug in positive 1. Positive 1 squared times 7 minus 80 is very, very negative. Okay, so that's the beauty of the first derivative test. I don't have to actually find the number. I just need to know if it's positive or negative. So once I have this done, I can figure out if my critical points are local mins, local maxes, or neithers. So my first one, negative 3.38, that is going to be a local max. It starts with a positive and ends with a negative. 0 is going to be neither. It starts with a negative and ends with a negative, so the sign doesn't change. Positive 3.38 will be a local minimum. It starts with a negative and ends with a positive. So we have one of each in this case. Max, neither, min. And then again, what's left is to draw them. So I'm going to do negative 4 and positive 4. We're going to guesstimate where positive and negative 2018 are. So I've got 0, 0. Maybe I'll make that dot a little bigger. Roughly 0, 0. Negative 4, 0, 4, 0. Negative 3.38 and a positive 2018 something. Negative 3.38. Positive 3.38 and negative, kind of inside my 2018, but that's fine. Once that we have those, we want to make sure that these guys make sense. So does it make sense that this guy is a maximum? Hopefully, yes. Does it make sense that this guy is a minimum? Again, hopefully, yes. I can see it, and I hope you can too. So as we go from negative infinity up to that first critical point, our function is increasing. Make sure you go through your 0. We go down to our 0. Our function has to flatten out, so make sure you don't try to make this like a straight line. It does flatten out a bit. And then goes down to our minimum, and then starts increasing again. Okay, so our picture should look something like that. And again, I'm not looking for perfection, it's just a sketch. So, just try your best. Make sure that it's increasing and decreasing where they're supposed to be. Make sure your max and mins are where they're supposed to be, and make sure your intercepts are where they're supposed to be. Okay? So let's try one last one. Y equals negative 10x cubed minus 13x squared minus 4x. So if I plug in x is 0, then I get out the origin again as one of my intercepts. So let's see what happens if y is 0. So hopefully we can see that there's a GCF of a negative x. So I can pull out the negative as well. If I do that, I'm left with 10x squared. It's not a very good squared, minus 13x minus 4. And now again with this quadratic in here, you can either use the quadratic formula or you can factor it. It is factorable. But you just have to be careful because the leading coefficient isn't a 1. Those guys should be positive. I took out the negative. So you have to remember how to factor when your leading coefficient isn't a 1. So there's the guess and check method, which I never recommend, and then there's the AC method. So the AC method, a little quick rundown, I want two numbers whose product is A times C, so 10 times 4. Product is 4, and sum is, product is 40, and sum is 13. So two numbers that multiply to 40 and add to 13 are 8 and 5. So what we do is we split up that 13. So I'm just going to ignore the negative x for right now. We split up the 13 into those two numbers, and then we factor by grouping. So my first group, 10x squared plus 5x, I can factor out a 5x. And I'm left with 2x plus 1. Bring down the plus sign. My second group, I can factor out a 4. And I'm left with 2x plus 1. I don't know why I put a 5 there. 2x plus 1. If what's inside your parentheses is the same, that means you did it correctly. And I'm kind of running out of room here, so I'm just going to go back to the top. So I have 0 equals my negative x, my what's in parentheses, 2x plus 1, and then everything else, so 5x plus 4. I solve each of those for 0, and I get 0, which I already knew, negative 1/2, and negative 4/5. Okay, so again, I have a cubic, so I can have up to 3 intercepts, which I do have. So there they are right there, the 0, 0, the negative 4/5, comma 0, the negative 1/2, comma 0. Okay, so my 3 intercepts. Now I need the critical points. So again, we'll start with y prime. So y prime equals negative 30x squared minus 26x minus 4. So my next step is set it equal to 0. Again, I'm going to factor out my GCF, which is a negative 2. So I've got a 15x squared minus 13x, plus 13x rather, plus 2. Okay. And then, again, this is factorable. Again, we're going to do the AC method. I want two numbers that multiply to 30, my A times C, and add to 13. Hopefully we can tell that that's 10 and 3. So my 15x squared, again, I'm going to ignore the negative 2 for right now to save space, plus 10x plus 3x plus 2. Factor my first group, I have a 5x. I'm left with 3x plus 2. My second group, there's nothing in common, so I'm going to factor out a 1. So I've got negative 2 times 3x plus 2 times 5x plus 1 equals 0. Again, set each of those factors to 0. Negative 2 is never 0. But when this guy is 0, I'm left with negative 2/3. And when this guy is 0, I'm left with negative 1/5. Okay, so those are the x values of my critical points. Again, I need to plug them into y to find the y values. So again, I'm not plugging it into y prime. I already know that's 0. I need to plug it into y because I need to graph it. So I want you guys to plug in negative 2/3 and then plug in negative 1/5, and you're going to get out something. And hopefully what you get out is negative 0.148 for the negative 2/3 and 0.36 for the negative 1/5. Now we have to decide whether these are local maxes, local mins, or neither. So I'll plot them. Again, it's really important that you plot them correctly. Negative 2/3 is on the left, negative 1/5 is on the right. And then again, we're going to go back to that factored form. Negative 2 times 3x plus 2 times 5x plus 1. It doesn't look very nice. Plus 1. Okay, so number to the left of negative 2/3, negative 1. If I plug in negative 1, negative 2 is always negative. If I plug in negative 1, negative 3 plus 2 is negative. And if I plug in negative 1 into 5x plus 1, I get out a negative. So a triple negative is negative. And then I'm going to just erase that. So that was from negative 1. Now if I use something between negative 2/3 and negative 1/5. So let's try negative 1/2. Okay, so negative 1/2, negative 2, still negative. Negative 1/2, 3x plus 2, that's going to be positive. And then plugging in negative 1/2 into 5x plus 1, that is negative. So a negative times a positive times a negative is positive. And then lastly, we'll pick a number bigger than negative 1/5. Again, 0 is a really good option. So negative 2 is still negative. If I plug in a 0 into 3x plus 2, I have a positive. And if I plug in 0 for 5x plus 1, I have a positive. And a negative times a positive times a positive is a negative. Which tells us that our critical point at negative 2/3 is a local minimum, because it starts with a negative and ends with a positive. And our critical point at negative 1/5 is a local max, because it starts at a positive and ends with a negative. And then again, we just have to plug it in. So I'm going to try to make these points a little bigger. There's my 1, my negative 1, negative 1, and 1. Again, I don't have to be exact, I just have to make sure it makes sense. So my origin, and then negative 1/2, comma 0, negative 4/5, comma 0. And then again, between any of my zeros, my x-intercepts should be a critical point. So my negative 2/3 is between my first two, and it's going to be somewhere over there. Negative 1/5 is between my second two. It's going to be somewhere over there. Okay, and then once I have those, again, I want to make sure that these guys make sense. So hopefully we can tell that this guy will be a minimum, this negative 2/3, and that negative 1/5 will be a maximum. And then we just connect them. Something like that. I'm a little off, but that's okay. Okay, so again, our derivatives were decreasing up to our first critical point, or our, first critical point, then increasing up to our second critical point, and then back to decreasing. So it matches with our first derivative test that we have. Okay, so, read through the book, try some out, and let me know if you have any questions. Thanks.